Okay, hello everyone. We're getting really close to the end of our discussion about stars. Okay, and then once we get done talking about stars, okay, we've already talked about galaxies. We talked about stars. We're going to get into solar systems and how a solar system forms. Once we're done that, we're going to move more into the geology stuff, right? So this is Earth and space science. So we're going to move more into the Earth component of it. So massive stars, right? We had the iron core. It collapsed, right? And as it collapsed, photodisintegration happened. Right? We then have neutrons, right? We create the neutron star, right? Spinning rapidly, emitting beams of radiation, right? And if those beams are detected by us, we called it a pulsar. What happens when stars get even bigger than that? When they collapse in a very dramatic way. And what you're seeing there on the title, let me move this out of the way here. Let me hide that. Right? We get black holes. So generally, we're looking at the fate of stars that are 20 to 25 times the mass of our sun. Next slide. So, neutron stars. If a neutron star gets big enough, right, that neutron degeneracy can't support all that mass. And that neutron star will collapse. It'll keep collapsing forever. So neutron stars cannot exceed 3 solar masses. Above this, the neutron stars cannot withstand gravity. So the force of gravity at a neutron star that is 3 times the size of our sun, or no, sorry, the size is the wrong word, 3 times the mass of our sun, right? The amount of gravity there is so strong, it overcomes neutron degeneracy, and the star will collapse forever. So what makes it a black hole? This equation here is the equation for escape velocity. What I mean by escape velocity is the speed you need to escape the gravity of an object. If we look at the basic formula, escape velocity is equal to the square root of 2 times the gravitational constant, right? Times the mass of the object divided by the radius of the object. So I want you to think of a fraction. Okay. So let me grab a pen here. That might make things easier. So 10 over 2. We're just talking about this fraction here. Let's say the numerator was 10, the denominator was 2. 10 divided by 2 gives you 5. Okay. That number 2 represents the radius of the object. But let's say that object is collapsing under gravity. So if our numerator was 10 and the radius of the object was 2, our escape velocity would be 5. So let's say it continues to collapse and I get 10 over 1. Right? 10 divided by 1 is 10. The escape velocity has increased as it collapses. Right? What if we go 10 over 0.1? Okay, it's collapsed even further to 0.1. So what is our escape velocity now? 10 divided by 0.1, and where I can't see, and I got to move this down so I can see it. Right? 10 divided by 0.1 is 100. Right? So what you should start noticing is as the radius gets smaller and smaller and smaller, that escape velocity, right, gets larger and larger and larger. So as the core keeps collapsing, let's say it got a lot smaller, and we got, 10 divided by 1,000. Okay, what is our escape velocity? Our escape velocity would be 10,000 now. The smaller and smaller the radius gets, the smaller and smaller the radius gets according to this formula, the greater and greater the escape velocity will become. So if an object has so much gravity that it is collapsing forever, that it's getting infinitely small, right? If it becomes infinitely small, its escape velocity will become infinitely large. Okay? So eventually, as the neutron star collapses to a point where it's becoming infinitely small, right? The escape velocity becomes infinitely large. It goes past the speed of light. You have to be traveling faster than the speed of light to escape the black hole. But in our universe, according to what we understand of physics right now, we can never exceed the speed of light. So, if an object collapses to a point where its escape velocity becomes the speed of light or greater, we now have a black hole. So, as the remnant collapses, the radius becomes smaller and smaller. If the denominator reaches a number that is infinitely small, this should say then, not then. This should be then. Then the escape velocity reaches a number infinitely large, right? That should be THEN, not than, right? So thus, as a neutron star collapses, the escape speed increases beyond the speed of light, and you have a black hole. So now the object has so much gravity that traveling at the speed of light, you still can't get away from that object. Okay? And in our universe, nothing is known to travel faster than the speed of light. There's no faster than light travel. So, supermassive star, you've got the iron core collapses into a neutron star, but if that neutron star has a mass 3 times that of our sun, gravity will overcome neutron degeneracy, right? Neutron degeneracy keeps the neutron star from collapsing, but if it's heavy enough, it's massive enough, it will overcome that neutron degeneracy and collapse and keep collapsing, right? And as the radius gets smaller and smaller, the escape velocity gets bigger and bigger. And once the escape velocity is greater than the speed of light, you have a black hole. So, a black hole means that there should be no type of radiation that can escape from a black hole. So, nothing on the electromagnetic spectrum should be able to escape. Right? There has been some theoretical ideas by Hawking, right? And I think it was even proved recently that there is some radiation that does escape. Right? It's called, Hawking radiation or Hawking evaporation, but that's way beyond what we would talk about. The next topic to discuss about black holes is the Schwarzschild radius. Right? So Schwarzschild, right, a physicist, did some maths, came up with this idea. So the Schwarzschild radius is the critical radius at which the escape speed would equal the speed of light. So using this formula, the known gravitational constant, the known mass of the object, and the radius, you can calculate it to a point where the escape speed is the speed of light, right? 3.00 times 10 to the 6 kilometers per second. Okay? So, Schwarzschild radius is a critical radius at which the escape speed would equal the speed of light. So the point of becoming a black hole. So if we were to take all the mass of Earth and shrink it down to a pea, 1 centimeter across, that would be a black hole. Its gravitational energy would be so compressed into such a small point that that 1 centimeter object would be a black hole. If we were to collapse Jupiter to 3 meters across, so like 9 feet across, it would be a black hole. A 3 solar mass neutron star, so the minimum threshold to become a black hole, will be 9 kilometers across. And the black hole is the object that's inside its own Schwarzschild radius, right? It's collapsing infinitely, but it's inside that radius. And that brings us to the idea of the event horizon. Right? So the event horizon is the surface of an imaginary sphere with the radius equal to the Schwarzschild radius. Okay? It is the point where the escape speed is equal to the speed of light. Okay? It's the point of no return, right, where we can't escape. Nothing goes faster than the speed of light. And we can consider that to be the surface of the black hole. Right? Once you pass the event horizon, there's absolutely no possible way you can come back. Right? Just before the event horizon, as long as you can travel at the speed of light, right, you can escape. But once you reach the event horizon, there is no escape. Okay, in these YouTube videos, you don't need to worry about this. I taught this stuff when we had a live class. It's not really too much of our curriculum, right, where we get into things like special relativity and start talking about some of Einstein's stuff. Don't worry about this. Just skip this, right? Special relativity, don't worry about it, right? Special relativity here, again, don't stress it. It starts talking about things like time dilation and whatnot. That's not necessary for this course. Okay, same here. It's talking about time dilation. It's interesting stuff. If you want to read it, go ahead. I am not going to be asking you about any of this. And we'll skip that one. Skip that one. Okay, skip here. Back to this. So the stuff on special relativity, don't worry about. So note, black holes are not vacuum cleaners sucking everything in. They have a mass. Because they have a mass, objects can orbit around a black hole. As long as they're far enough out and they're moving quick enough, they can establish a stable orbit, just like we orbit the sun or the moon orbits the Earth. Right? Objects can orbit a black hole. If they get too close, right, they can be pulled in, but objects can establish a stable orbit around a black hole. The other thing to note, black holes can accrete matter, meaning they can gather matter from space, right? As things get too close, they get pulled in. So its mass and its radius can increase slowly over time. So black holes can grow. They can become more massive over time. Okay? They become more massive, right? Black holes have been known to absorb other black holes and create larger and larger black holes. Right? We get supermassive black holes that are found at the center of galaxies, like we have a supermassive black hole found at the center of our galaxy. Okay, this here, tidal forces, kind of just talking about the gravity in a black hole. So matter falling into a black hole will be stretched and compressed. They call it spaghettification, where matter will be stretched out, right, by the intense gravity. It will also be accelerated to extremely high speeds due to that gravity. So someone falling feet first into a black hole will be stretched and compressed laterally, right, with the force of gravity at your feet being way stronger than the force of gravity at your head. So you're stretched laterally to the point where you would be ripped apart. The end result, right, is all this debris is traveling extremely fast. It's approaching the speed of light as it's being pulled into the black hole, right? And we get intense heat and we get intense friction, right, from all the particles zooming around the black hole at, near the speed of light. So the matter that's spinning around a black hole, it hasn't yet gone past the event horizon, right? But it's moving so fast and there's so much friction, it gets extremely hot. And because it gets hot, it gives off radiation. Okay, so because it can give off radiation, it can be seen, right? And scientists have seen, we've now visualized black holes. This image here is theoretically what we think a black hole will look like. Okay, and on the D2L, I'm going to post the image that they did find, right? That they did determine was the black hole. But here we can see the accretion disk around the black hole glowing because it's super hot. Okay? We see this vertical ring around the black hole because the black hole's gravity is actually bending light, and the light, so this disk is going all the way around 360 degrees around the black hole, right? This disk that you see around it is due to the light that it's giving off being bent and projected towards us from the black hole. And I'm gonna post a video as well into your D2L that will be able to explain this. I need to be in front of you to explain this, but the gentleman on YouTube, right, he has it set up really well that he can explain why we see this image, and that will give you some more information. I'm not really going to test you much on a black hole, right? I need you to know what it is, why it forms, and you should be able to comment on this equation, okay? That as the radius gets infinitely small, the escape velocity gets infinitely large, right? That's the main idea. If a denominator becomes infinitely small, right, the number becomes infinitely large. Okay. Do not worry about the special relativity stuff. Read it if you're interested, right? It is very interesting, but I am not going to. We're not going to get into it. This is something that we would need to be discussing in person. It's not going to. Excuse me. It's not going to work well in this format. Okay, so I'll post all that stuff up. Bell's about to ring. I'm going to have to teach a class in person, my grade 9s, in a few minutes. So once I'm done teaching my grade 9s, I'll post this video. I'll post that YouTube video and the images of what we've actually seen of a black hole, right? And I'll also kind of discuss what I expect of you over the next few days. Okie dokie.